Okay, there's a couple more topics from 9.5 that we didn't get to previously. First, polar arc length. This one is going to be a pretty easy formula to use. The formula for polar arc length, usually use S, is the integral from alpha to beta. Just use those for A and B since we're in polar. And those are going to be angles. The square root of r squared plus dr d theta squared, all d theta. And that's, it's just take the function and square it, take its derivative and square it, square root that whole thing, integrate from alpha to beta. And as a quick example, we're going to use this function in the second problem, but find the perimeter of 3 times 1 plus sine theta. So in my calculator, I have that graphed. It's kind of I think it's called a cardioid because it's kind of heart-shaped. The perimeter, honestly, I don't know if perimeter is technically the term. Perimeter usually implies straight sides, but circumference isn't really the word either, so I just went with perimeter because that means all the way around the outside edge. So one thing that's important when you're dealing with these graphs is you need to know what it is, what window traces a full revolution of the graph. If the argument of your trig function, in this case sine, is just theta, then that means it's going to go from 0 to 2 pi. In some of the ones we were doing with the areas of the petals, you had to play around with those numbers and see what would create one full drawing of the graph before it starts retracing itself. So your calculator should naturally go from 0 to 2 pi like this one does. You can see if you changed it from 0 to pi and graphed it, you would just get part of the shape. If you went from anything beyond pi, you would get more than that. So 0 to 2 pi will trace it one time over. And you can just kind of experiment if you're not sure. I don't know another way to tell you other than just try less than 2 pi and see if you can get the full shape. One other thing, if you get into some small windows, one of our problems in class was a 5-petaled rose that if you were just graphing it from 0 to pi over 10, it didn't quite look right. That's because what your graph does is it plugs in a theta, it gets a point, and it just connects the dots. This theta step, that 0.13, I think that's pi over 24 or some number like that in decimal form. If you make that number too big, like 1, then it's going to plug in 1, 2, 3, 4, 5, and 6 and connect the dots. You can see what that does to your graph. So if you try to do a polar graph and you get a shape that's like jagged and looks like it's just a few points, make your theta step smaller, like 0.1 or even 0.01. It takes it longer to draw, but that gives you a more detailed picture. 0.1 is at least detailed enough to where the graphics of your calculator are going to be, it's going to give you the best it can. So back to the issue, we were trying to find the how long it is all the way around this shape. So let's do that. All right, polar arc length, alpha to beta, that's 0 to 2 pi. We just confirmed that 0 to 2 pi traces this thing once. Okay, so then we need to do the function squared and then the function's derivative squared. All right, this function's derivative will be 3 times, the derivative of 1 is 0, the derivative of sine theta is cosine theta, and that needs to be squared d theta. So this expression should be the perimeter, or the arc length, all the way around the full shape. And sometimes they'll say, what's the arc length of one petal or whatever, but this is, I asked you for the whole time, the whole perimeter of the shape. So remember, when you're doing your calculator work, that's almost always going to be done in regular mode. We just pretend this is an integral that's in terms of x. Even though it was generated by a polar graph, that's okay. So the way we integrate is math 9. All right, so I'm integrating a big square root. The first thing inside that square root is 3 times 1 plus sine of x and a bunch of parentheses get opened up. So that closes the sign, that closes the 1 plus, that closes the first thing to be squared, and then square that. The parentheses, in my opinion, are the most difficult part of this. Plus 3 cosine 3 cosine of x. Got to close after the x, close for the 3, square it all. Now close the whole square root, and that should be our function. So I'm going to integrate with respect to x from 0 to 2 pi. And it'll probably take it a minute to think, and 24. All right, so it worked out nice and even, which probably we could have integrated this one maybe without, but that's all right. You can do it in your calculator. So 24. Now I just made this problem up so I don't have a key to tell me if that's right or not. So I'm going to go back to the picture and see if 24 is reasonable. Always a good idea when you don't have an answer. So I'm going to go back to my graph in polar. And now if I zoom in square, that'll make sure my x's and y's aren't distorted at all. And I'm looking for 24, and you can see, this is basically 1 unit. Kind of hard to show, but you can see how big 1 is from there to there. So if you just kind of, 1, 2, 3, 4, 5, 6, 7, just kind of look and see, it's reasonable that that side would be 12 and the other side would be 12, which it is. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's about right. Now, like I said in class, this doesn't necessarily tell you that 24 is right, but if you had something like 48, it would tell you that that was wrong. So this will eliminate mistakes, not necessarily give you the exact right answer by estimating in this way. Okay, so that's one thing, polar arc length. And next topic is, we did areas. I'm going to call this one funny areas. There's a question in your book that says, what's the common interior of this graph and the same graph with a minus? If you graph both of those, you get kind of 2 of these heart shapes, one on top of the other. And common interior just means the area that's inside of both of them. So I'm going to adjust my window a little bit so we can see that area better. That'll work. So both of these heart shapes get traced out, and the common interior, this is the top heart shape, and this is the bottom one. So the common interior is just, these just eyeglass looking shape right here. It looks like sunglasses. So I'm trying to figure that one out. Almost always in one of these situations, you can use symmetry. If I can figure out how much this is, I can multiply it by 4 to get the full common area. So let's try to figure out how much area that is, or how much area this is, or any one of those. If I can figure that out, I can multiply by 4 and see what the total area is. So whichever one of those is most convenient, I'm going to deal with. So first of all, finding that red shaded area right there only involves one of these functions. So let's get rid of the top one. If I graph just the bottom one, there I can find that red shaded area just based on the bottom one. And kind of mess around with the window to see what traces, what thetas trace out that area that we're interested in. It appears to be drawn, you change something and change it back, it'll draw it again. So watch from the beginning when you draw. Oh, it didn't draw it. Hang on a second. Change the function and change it back. So it starts by drawing the first little part over here. So from 0 to whatever that is will give me that area. So I'm just going to kind of play with the window and see, what if I go from 0 to just pi? So that's going to give me the top. So that gave me twice as much area as I wanted. So it looks like 0 to pi over 2 is going to give me the area that I want. Okay, so now just by messing around with the calculator, I've discovered that I need to find the area from 0 to pi over 2 of one of the shapes, and then I'm going to multiply it by 4. I'm going to pause and fill this in to keep this video short, so I'll be right back. So what I discovered in my calculator is that I need to quadruple the area generated by the bottom graph from 0 to pi over 2. So the area generated by that is the area formula that we covered in the last video. 1/2 times the integral of the r squared from whatever angle you start to whatever angle you stop. So back in my calculator, all of this type of stuff is done in regular mode. So math 9, excuse me, not that, math 9, what I want to integrate is this function, which is 3 times 1 minus sine x, close the sine, close the 1 minus, close the 3, square all of that, with respect to x, from 0 to pi over 2. And I get 3.2. So remember, that's the area under the 1 graph. That's kind of a fourth of those little sunglasses. Let's just call that 3 point, let's round it to 3.2. So this is 4 times a half of 3.2. In other words, the 4 and the 2 make a 2. 3.2 gives us about 6.4 total. And like normal, I would like to check and see if this is reasonable to eliminate any mistakes. So again, I'm going to switch back again. Look at my actual graph, polar. Put my other one back in. 3 times 1 plus sine of theta. And here's the area. Now I need to get my stopping point back to 2 pi to draw the full shape. So that middle sunglasses area should be about 6 units. So, this is 1 right there in the y direction. So this much, that much area right there is about 1 square unit. So we've got almost 1 there. Put this together, we get about 2. Add in this, and you get, about 3 and change on the left, which means there's about 3 and change on the right, which means our 6.4 is a reasonable number. I don't know, I could have made a small mistake and the answer is really 7 or 5.5. It wouldn't tell me a mistake like that, but it would tell me if I had a ridiculous answer. So keep that in mind. Look at the picture for those reasons. It's about the only use the polar graphs have on your calculator. So that'll wrap up the polar discussion, and we will be testing soon. So be ready for that. Young out.